Good morning, friends. So it occurred to me that there's actually a better PewDiePie format to use for this week's video.
Leave your entries in the subreddit pros, and I'll watch submissions in the next episode of LWIAY.
Alright, so last Friday we went through a series of problems, so sort of more advanced problems on molarity. And we had a little bit of troubles along the way, so I'd like to go over the solutions with you guys now. Alright, so our first problem was this one. In a 1 liter beaker, 203 ml of 0.307 molar ammonium chromate was mixed with 137 ml of 0.269 molar chromium 3 nitrite to produce ammonium nitrite and chromium 3 chromate. If the percent yield of the reaction was 88%, what mass of chromium 3 chromate was isolated? Alright, so when I'm going through a problem, I usually like to look out for some keywords to let me know what kind of problem I'm looking at and what approach I should be using. So the fact that we're mixing two things together and we're producing something else, as you can see here and here, that's telling me, okay, I'm looking at a reaction type problem, probably stoichiometry. So with that, you're going to always want to start with the balanced equation. So let's do that first. Okay, so this problem is a pretty good reminder that you are still expected to know the polyatomic ions. On the quiz, I'll try to make sure it doesn't take up too much of your time, but be aware that's still a thing that you're supposed to know. Alright, so let's write out this equation. We've got, we've got ammonium on here, so NH4, and then mix with chromate CrO4, and then ammonium is just a +1 charge, so we need 2 of those. Then it goes to chromium nitrite, so nitrite is NO2 instead of NO3, like nitrate. So because we're told that it's chromium 3, we need 3 of those to balance out the charge. Then that goes to ammonium nitrite, so NH4NO3, so that should be balanced, plus chromium 3 chromate. So we've got a chromium, and then we've got the chromate ion, and then to balance out the charges, we have 3 of these and 2 of these. Okay, so for balancing stuff with polyatomic ions, to make it easier on yourself, we don't need to separate everything out into nitrogen, hydrogen, oxygen. We can keep the polyatomic ions together, and that should simplify things a good bit. So we're going to have our ammonium here, our chromate, our chromium, and nitrite. Okay, so as we get started here, I'm just going to count off what's on each side. So we've got 2 of these, 1 of these, 1 chromium, and 3 nitrites. On this end, we've got just 1 ammonium, 1, oh my gosh, see, I messed up already. I'm so used to nitrates that I automatically put a 2 on there, but it's sorry, I don't put a 3, but it should be a 2. So NO2. I'm glad I caught that. So that's just 1 of the nitrites, and then 2 chromiums and 3 chromates. Okay, so to balance this out, all right, I'm gonna just start with 2 on the chromate. So that's 2 on the chromium. Man, this problem's a tongue twister. So 2 chromiums now, and that will give me also 6 of the nitrites. Okay, my tongue and my pen aren't keeping up with each other. Okay, 2 and 6 now. And so now we need to balance. All right, chromate. There's 3 on this side, just 1 on this side. So I'm going to add a 3 front here. So that will give us 3 of these and also 6 of the ammoniums. So that will be 6 now. Okay, so it looks like these are good. All we need to do is add a 6 in front of here to balance the ammonium and the nitrite. All right, so that's our balanced equation. Okay, so once you have the balanced equation, I like to kind of use the balanced equation as a sort of roadmap to the rest of the problem. So I like to label my balanced equation with what I'm given and where I'm trying to get to. So we're told that we've got 203 mils of ammonium chromate. So 203 mils, a lot of times, especially if it's a molarity problem, I like to save time and just automatically convert it over to liters. So we've got 203 mils of that and 0.307 molar of the solution. Okay, so this solution is now mixed with 137 mils of 0.269 molar chromium-3 nitrite to produce ammonium nitrite and chromium-3 chromate. If the percent yield of the reaction is 88%, what mass of chromium-3 chromate was isolated? So we've got this whole percent yield thing, which we'll take care of a little bit later, but basically what they're looking for is the mass of chromium-3 chromate. That's what we're trying to get to. So this in grams. I like to also label the unit if I can, because that'll remind me to not miss points by leaving out a conversion. Okay, so we know what we're given, we know what we're trying to get to. At this point, we've been doing molarity for a little bit. As soon as you see a volume and a molarity, you know you can get to moles. And that's really the key for all these stoichiometry problems. You will need to get to moles somehow. If you're given mass, you want to go with molar mass. If you're given molarity in liters, you can use, the molarity equation to get to moles. In a little bit, we're going to be, well, I guess today, technically, we're going to be learning about gas laws and all that, and that will be a whole nother way to get to moles. But whatever you do, get to moles so that you can use the stoichiometry of the problem. So let's do that. And, oh, one more thing to note about our roadmap here. Look at the pattern, right? So we're given amounts of 2 of the starting materials, and we're asked about the product. So that kind of pattern really tells me this is a limiting reagent type problem. Because we don't really know which one of these is going to give us the correct mass of the product. So for limiting reagent problems, my strategy is just go with what they're giving you and calculate the mass that you'll get from each of the 2 different starting materials. And whichever one is smaller, that is your true amount of product that you're forming. So let's do that on the next page. All right, so we're going to start with the ammonium chromate, the first one they gave you. So we have 0.203 liters of the ammonium chromate, and from the molarity, that 0.307 moles of, I'm going to run out of room here, ammonium chromate give you, are found in every liter of ammonium chromate. Okay, then now we're in moles, so we can use the stoichiometry of the balanced equation. So for every 3 moles of ammonium chromate, we produce 1 mole of our product. So remember, from our roadmap, we're trying to get to here, right? Okay, so we got moles, and then because we know we want it in grams, as we see here, we're going to do a quick conversion and get that into grams. So for every mole of chromium 3 chromate, the molar mass of chromium 3 chromate, this is probably the most annoying part of this problem, is actually calculating this out. So you would have to go to the periodic table and add up, 2 chromium atoms from here, and then 3 chromium atoms from the chromate, and 3 times 4, 12 oxygen atoms. So you would have to add all those up and get the molar mass that way. I'm not going to show that, but that's what you would do. So the molar mass ends up being around 452.00 grams. Okay, so yeah, now we've got to where we want to be, grams of chromium 2 chromate. So if you work all that out, the answer will end up being 9.39 grams of your product, so chromium 3 chromate. Alright, so that's from ammonium chromate. So now we've got to go back and check what happens when we use our other starting material. Alright, so now we do the same with the other starting material, which is chromium 3 nitrate. So exact same process, starting with the liters, using the moles to convert, the molarity to convert over to moles. Moles of chromium nitrate, and 1 liter. And then just to save time, I'm not really going to show all of the labels for everything, but basically now we're going to do the mole ratios. So basically 2 moles of the chromium 3 nitrite go into 1 mole of our product. So starting material, product, yeah, I'm just getting tired of writing out the whole polyatomic ion on this computer, but that's fine, as long as we got the right mole ratio. Okay, so moles of chromium nitrite, and then there's a ratio, 2 moles of chromium nitrite go to 1 mole of chromium 3 chromate, and then again, it's the molar mass. So for in every mole of this product that we're looking for, it is the molar mass, which is 452.0 grams. And once you work that all out on your calculator, you're going to come up with 8.33 grams. So you'll notice that this is the lower amount. Because this is the lower amount, this is the actual amount that gets produced. And this also means that chromium 3 nitrite is the limiting reagent in this case. But yeah, so now we know, okay, so I said this is the actual amount made or produced, but you got to remember that this is in theory. Once we get into the lab, things, are less than perfect, things are less than ideal, so usually we get a actual percent yield out of this. So let's do the percent yield part of this problem. Alright, so percent yield of the reaction is 88%. What mass of chromium 3 chromate was isolated? Alright, so we just calculated out that in theory, we should be getting 8.33 grams. But in lab, things go wrong. So what this is telling you here, the percent yield of the reaction is telling you that we only got 88% of what we expected to get. So in theory, if everything was perfect, we were absolutely awesome with all our techniques, and so forth, the maximum we could ever get would be 8.33 grams. But what the percent yield is telling us is that we only got 88% of that. So, the quick way to do it is just multiply your theoretical yield by the percent yield as a decimal. So just convert your percent yield into a decimal and multiply your theoretical yield by that, and you will get your actual yield. So actual yield turns out to be 7.33 grams. So where this is coming from is sort of the percent yield problem. So percent yield equation. So percent yield is defined as the actual yield my computer's having a hard time catching up with me. So actual yield over theoretical yield. And that's times 100%. So basically what I just did was rearrange this around. So we're given a percent yield. We calculate out the we're given a percent yield and we calculate out the theoretical yield based on the stoichiometry. So they're asking us for the actual yield. So essentially you just kind of rearrange this. You're multiplying the theoretical yield times the percent yield and also divided by 100. That will give you your actual yield, but I just kind of did a bit of a shortcut there. But in the end, this is your final answer. 7.33 grams are actually produced. All right, moving on to our next problem. So this one has a mixture containing only sodium chloride and iron nitrate. This mixture, there's a 4.56 gram sample of this mixture and it's dissolved in water. And then an excess of sodium hydroxide is added, producing a precipitate of iron hydroxide. The precipitate is filtered, dried, and weighed, and its mass is 0.107 grams. Calculate the mass percent of iron nitrate in the sample. Sorry, I got cut off a bit there. Okay, so this problem honestly is not that hard, but they throw in a red herring there that kind of can throw you off a bit. So first of all, we've got the mixture. Mixture contains only sodium chloride and iron nitrate. So basically this looks like this. We've got our sodium chloride and iron nitrate. So these two things, these two solids are mixed together in whatever container, and that is what eventually gets dissolved and passed on to the next reaction. So got this mixture. Its total mass of this mixture is total mass is 0.456 grams. Okay, so that would be the mass of sodium chloride plus the iron nitrate. Now, we're told that this mixture is dissolved and then it reacts with sodium hydroxide. So essentially we've got this mixture here going down, and then we've got our sodium chloride plus the iron nitrate plus sodium hydroxide. So we're reacting all those together and we produce a precipitate. They actually tell you what the precipitate is. It's iron hydroxide. Okay. So because they tell you the precipitate is iron hydroxide, and you can also figure this out using solubility rules, that means that your leftover ions are going to be sodium nitrate, just the leftover ions there, and also NaCl. So the important thing here to realize is the NaCl isn't going to do anything in the reaction. And that's because this is a precipitation reaction, and we know from our solubility rules that sodium is soluble with almost basically everything. Chlorine is soluble with almost everything except for a few exceptions, and none of those exceptions are in here. So they're just going to be floating around as ions in the background while this main reaction is going on. So our mixture is here, but the main reaction is going on here. So basically, don't worry about the sodium chloride. It's just hanging out there. We're only going to take into account when we have to figure the total mass, the percent mass from the total mass. Okay? So focusing in on the iron nitrate plus sodium hydroxide, what information are we given? So we know that we produce 0.107 grams of our product. And what do we need to know? We're calculating the mass of iron nitrate. So we're interested in mass of iron nitrate. So that's what we're going to find first, and then we're going to convert that over into a mass percent. All right. Okay, so from our equation here, remember this stoichiometry problem, so always start with a balanced reaction. So we have our basic reaction here, we're discarding the sodium chloride, but how do we balance it? So if we do a quick look over here, it's nearly balanced, except we're going to need, let's see, so we've got 3 nitrates, well we only got 1 here, so we're going to add a 3 over here. And then we've got 3 hydroxides, but only 1 over here. We're going to add a 3 here. So that should be balanced. Yeah, 3 sodiums, 3 hydroxides, and 3 nitrates, and just 1 iron. Okay, so now that we're balanced, we can go ahead and start with the stoichiometry. So again, we're starting with our iron hydroxide here. So we're going to go ahead and work from there. So 0.107 grams of our iron hydroxide. That's getting converted over into moles. Remember, always want to get to moles, in this case with our molar mass. So we've got 106.867 grams of iron hydroxide in every mole. That's just from the periodic table. Okay, and then now we are going to use a mole ratio. So we're going from our iron hydroxide here, and we're trying to end up with iron nitrate. So that's just an easy 1-to-1 mole relationship. So 1 mole of iron hydroxide goes to 1 mole of iron nitrate. I'm just going to label them as a product and a starting material here, just to make it easier for myself writing on this screen. Okay, and then we want it in grams, so conversion back out to grams using the molar mass of your starting material, which is the iron nitrate. So that comes out to be 241.86 grams. Okay, so we've got 241.86 grams per mole of iron nitrate. And once you calculate it out, everything should cancel. And we are left with 0.242 grams of the iron nitrate. Okay, so and now we're going to get over to our last final. Okay, and then the last step is just getting the mass percent. So as I'm showing here, mass percent is really easy. It's basically the only reason we had the sodium chloride in this example, right? The sodium chloride basically was just there because, you know, it's giving us this total mass here in this mixture. So the total mass is 0.456 grams, which is clearly more than what we calculated for iron nitrate. So that extra mass in there is from the sodium chloride. So to get the mass percent, really easy, just a basic part over whole percentage problem. So you have your mass of your iron nitrate, and then you divide by the total mass down here, times 100% to get it to be a percent, and you end up with 53.1% as your final answer. So yeah, not a bad problem overall, just kind of a red herring with the sodium chloride. So you have to realize, because it's completely soluble, it's not participating at all in the precipitation reaction, so you don't have to worry about it. All right, problem 3. This is the one that a lot of you guys got stuck on last time because it's a pretty good problem. So it'll ask you to combine 2 different reactions and get the information from both of them to get your final answer. So this says a student added 50 ml of sodium hydroxide solution to 100 ml of 0.400 molar HCl. The solution was then treated with an excess of aqueous chromium-3 nitrate, resulting in the formation of 0.206 grams of precipitate. Determine the concentration of the NaOH solution. Okay, so like I mentioned before, we have two reactions going on here. So how you can tell that is by looking at the reactants. They're telling you. So we've got NaOH here, strong base. So we know that a strong base is going to react with a strong acid, such as HCl, to form water plus all the counter ion as a salt. Okay, so that's one reaction right there. But then this goes on and says that chromium-3 nitrate was added, resulting in the formation of a precipitate. So that's telling you that there's a second precipitation reaction going on here. So our first step is really just to write out what's going on here so that we can, continue on with the problem. Okay, so let's write out what we know. So first of all, the sodium hydroxide with the HCl, that's pretty simple. So we've got our NaOH reacting with HCl. So we know that the hydroxide is going to come off and it's going to react with the proton that's going to come off of the HCl, and that's going to give us H2O, or water. And then the leftover sodium and chloride are just going to be hanging out. So this one's actually already balanced, so that's pretty nice. And yeah, so that's our first reaction. And the information we're given for this reaction is we know we've got 50 mils of NaOH, and we know we've got 100 mils of the HCl, and it's 0.400 molar. But we don't know the concentration of the NaOH, so that's what we're trying to get towards. However, there's more. As we know that this problem goes on, it says that the solution was then treated with an excess of aqueous chromium-3 nitrate, resulting in the formation of 2.06 grams of precipitate. All right, so I'm going to kind of lay out the skeleton for a precipitation reaction, right? So we usually got two soluble aqueous solutions. They're going over and they're forming a solid precipitate plus the aqueous counter ions. Aqueous. These guys should be aqueous as well. So that's a typical precipitation reaction. And we know that one of these reactants is going to be chromium nitrate. Okay, and 3. All right, so we know one of those things is going to be chromium nitrate, and we know a solid or precipitate is forming at the end. All right, so we need to keep in mind that it says that the solution was treated. So when they say the solution, that means everything. So whatever happened here, all of that is now getting treated with your chromium nitrate. And another important note is that we're never told that we're never told what is limiting in this first part of the problem. So we are not told what is in excess or what is limiting. So what that means is that any of these things in the first reaction could potentially end up reacting in the second reaction, because we don't know if sodium hydroxide is limiting or HCl is limiting, so some of it may be still left over at the end of the reaction. All right, so now we have to apply our solubility rules. We know that chromium nitrate is going to react with something, and it's going to form a precipitate. So so we need to think, what in this entire whole what in this whole set of equations could possibly react with chromium and produce a solid precipitate? When you look at your solubility rules, you'll quickly see that there's only one option. A lot of you guys thought it was chloride, which kind of makes sense because, there's chloride here in the sodium chloride kind of left over at the end of that reaction. So it kind of makes sense, like, okay, it's like a series. You take the sodium chloride and now you react it with the chromium nitrate. But the problem is, if you look at the solubility rules, chloride is soluble with most things except for a few exceptions, and chromium is not one of them. So chromium chloride is actually soluble in water. So the chloride is out. So that really leaves us with only one other option. Obviously nitrate right now with chromium is aqueous, so that's not going to be in the precipitate. So the only thing that could form a precipitate would be the hydroxide. So when you realize that, then you know that sodium hydroxide must have been in excess because there's a precipitate forming, so there must be some hydroxide that can react with the chromium nitrate here. So if the sodium hydroxide is what's reacting, sodium hydroxide here, we can finish off this equation by showing that, okay, so the precipitate that's forming must be chromium hydroxide. So remember that hydroxides are relatively insoluble. They're just soluble with few things such as sodium, calcium, that kind of thing. Okay, so chromium hydroxide, and because this is chromium 3 hydroxide, yeah, so this chromium 3 hydroxide, we're going to need a 3 there. And whatever's left over is obviously just the sodium and the nitrate. So NaNO3. Okay, now we make sure it's balanced. So here we've got 3 nitrates, but there we've only got 1. So let's fill that in. So we're going to need a 3 here, and as well a 3 over here to make sure everything's balanced. Okay, so now I got 3 sodiums, check, 3 hydroxides, check, and then 3 nitrates and 1 chromium. All right, we're good. So now we have the second balance equation. And another important thing to note is in the problem, they do tell us that the chromium 3 nitrate is in excess. So for the first reaction, we were not told what is in excess, but the second reaction, we are told that this is in excess. So what does that mean? So if you have extra chromium nitrate, that means you're going to completely react out all of the sodium hydroxide. So essentially, we've got a certain amount of sodium hydroxide and we put it through 2 reactions. The first reaction with the acid used up some of the sodium hydroxide, but not all of it, because there's still some left over to react in the second reaction. Now in the second reaction though, we made sure that we put in more chromium nitrate than we needed so that all of the sodium hydroxide reacted. So basically all of the sodium hydroxide in this original solution here had to react in both of these equations. So if we find the amount of sodium hydroxide that was formed in the first reaction, add it to the amount of sodium hydroxide that was reacted in the second reaction. Sorry, I'm not sure if I said that right, but basically you're trying to get the amount of sodium hydroxide that's formed from each of these reactions, then add them together. You're going to have the total moles of sodium hydroxide that were originally there. Then you would just take your volume here and have moles divided by volume that should equal your molarity. Okay, so that's the general setup. Now let's go ahead and work through the problem. All right, sorry I had to re-record this page, but what I was just showing here is that we need to calculate the moles of NaOH from each of the reactions so that you can basically tell the total amount of sodium hydroxide that was used up. So first, from the precipitation reaction, we used the amount of precipitate that's given to us, 2.066 grams of the precipitate, and then you have to get the moles before you get to stoichiometry. So in this case, because you're giving a mass, you use the molar mass of chromium hydroxide, and then you get to moles. Now we're interested in getting to sodium hydroxide, so using the mole ratio, we know that for every 1 mole of chromium hydroxide, you need 3 moles of the NaOH. So that ends up giving you 6.00 times 10 to the negative 2 moles. Now for the sodium hydroxide in the acid-base reaction, again, same principle, you want to get to moles before you use the stoichiometry. So In this case, because we're given volume and molarity, we're going to use that to get the moles instead. So we've got 0.100 liters of HCl. So we're multiplying that by the molarity of the HCl. Then we're using the mole ratio, which is just 1:1. And then that will give you 4.00 times 10 to the negative 2 moles in the acid-base reaction. So to get the total, we just need to add these two together. All right, so we found individual amounts of moles, and now it's just a really easy calculation to get the molarity. Okay, so remember that molarity equals moles of your solute, which in this case is NaOH, over liters of solution, specifically the NaOH solution. Okay, so we just found the total amount of moles that were in the original NaOH solution. So we're talking about this guy now. So we found the total number of moles by checking each of the two reactions. So we know it's 6.00 times 10 to the negative 2 moles plus the 4.00 times 10 to the negative 2 moles. Okay. So those two together would be the total moles of NaOH that were in this original NaOH solution. And then from here, we know what the volume is, 50.0 mils. Convert that to liters. That's really important to make sure you get the right number. So 0.0500 liters. And yeah, once you get this into your calculator and calculate it all out, it should come out to a nice round 2.00 molar. And that is your final answer for this problem. Alright, last problem. We didn't really get to this one last Friday. That's a pretty cool problem. So, carminic acid contains only carbon, hydrogen, and oxygen. It was commonly used as a dye in the first half of the 19th century. It is 53.66% carbon and 4.09% hydrogen by mass. A titration required 18.02 mils of 0.0406 molar sodium hydroxide to neutralize 0.3602 grams of carminic acid. Assuming there's only one acidic hydrogen per molecule, what is the molecular formula of carminic acid? So, as you might have guessed, there are actually two parts to this problem. The percent masses here tell you it's a percent mass problem initially, and then they're giving us some information about a titration here. And as you can see, they're asking for the molecular formula of carminic acid. And you know that from percent masses, you can get the empirical formula straight off, but in order to get the molecular formula, you need more information. You need the molar mass. So essentially, we're going to get the empirical formula from the first part of the problem, and then we're going to get molar mass from the second part of the problem so that you can use that to get the molecular formula. Okay, so I'm not really going to cover the first part of the problem since it's just exactly like in my last video when we went over percent masses. It's the exact same process. You can use the standard 100 gram method to find the empirical formula. So assume 100 grams. We've got 53.66 grams of carbon, 4.09 grams of hydrogen. Subtract from 100 to find the grams of oxygen, and so forth. So then you would get the moles divided by the smallest number of moles, and then figure out the ratio from there. So it is, if you do want to try this on your own, there is a weird thing with this one where, like, when you divide by the smallest number of moles, it's not going to give you nice numbers. So then you have to do this weird thing where you divide everything by divide moles by well, I guess the mole ratios by 0.406 to get nice numbers. But this is weird. We're not going to ask you to do something like this on a quiz or exam. So as long as you know the basic standard 100 gram method to find empirical formula, that should be fine. So just make sure you can do that. Don't worry about having to deal with weird numbers of mole ratios. Okay, so assuming we've got the empirical formula, which is C22H20O13, now we need to figure out what the molecular formula is. And like I mentioned, we're now going to use this titration reaction. So let's start out with writing out the formula, which I guess we can do now since we've got an empirical formula, but then we don't know what the molecular formula is, so how do we even balance that? The key here is because we know it's going to be an acid-base reaction, right? We know we're dealing with carminic acid, and we've got a strong base, which is sodium hydroxide. So it's just going to be an acid-base neutralization reaction. You can see that we're neutralizing there as well as a tip-off. So, and also, I guess one more important note, you get to assume that there's only one acidic hydrogen per molecule. So using that information, you can write out a generalized formula. And what I mean by that is you can just write out carminic acid as a symbol. So you can say HA will stand for carminic acid. So you've got your acidic proton out front, the rest of carminic acid, whatever it is, in the back. You're reacting that with sodium hydroxide. And just like all other neutralization reactions, you're going to get to water and the leftover counterions, which would be sodium in this case, and whatever the rest of carminic acid is. So we're not really going to worry about the rest of carminic acid because that's what's important for this equation. So the information they're giving us is 18.02 mils of 0.0406 molar sodium hydroxide. And that's what's required to neutralize 0.3602 grams of carminic acid. And remember, our goal is to get molecular formula. So, and again, we have the empirical formula, but to get molecular formula, we need the molar mass. And molar mass, of course, is just grams over moles. So if you can get the ratio of that for a particular sample, then you're good. So we've got the grams of carminic acid here. Now we just need to get the moles, and that's where this part here is going to come in. So let's calculate the moles of carminic acid from the information they gave us here with sodium hydroxide. So let's get to moles of sodium hydroxide. So it's starting out with 0.01802 mils. Sorry, not mils. I just converted that in my head, liters of sodium hydroxide. And we know that there's 0.0406 moles of sodium hydroxide. So that is the molarity here. Okay, so now we need to know how does the molarity of the sodium hydroxide relate to the carminic acid. So in this case, we don't know what the rest of carminic acid is doing, but we know it's going to end up the same. So this is already balanced, essentially, for the important parts, which is the hydrogen here, the hydroxide here, becoming water here. So it's a 1-to-1 mole ratio. 1 mole of sodium hydroxide goes to 1 mole of HA. So yeah, we're already at moles of HA, which is exactly what we wanted to get to. So if you go ahead and calculate this out, it will end up being 7.32 times 10 to the negative 4 moles of carminic acid. All right, and once you've got that, all you need to do is divide by the mass that was given up here to get your molar mass. All right, guys, final stretch. So had to move a little bit because I had to go to a meeting. But so this is what we've got now. We've got the moles of carminic acid, 7.32 times 10 to the negative 4. And we already have the mass of carminic acid, which is given to us in the problem. So since molar mass is grams over moles, all we need to do now is divide these two by each other, and then you would get your molar mass. So what this comes out to, is roughly 492 grams per mole. All right, so how does this help us get the molecular formula? Well, the empirical formula, as we'd already worked out, is C22H10 H20, and then O13. So this was the empirical formula. Now, if you went ahead and calculated what the molar mass of this is, 22 times 12.01, 20 times 1.008, plus 13 times 16, you would actually end up with something right around 492 grams per mole. So what that means is this empirical formula actually is also the molecular formula because these two things are the same. So that means our final answer is C22, H20, O13. All right, we're done. Just some last notes on this problem. So you'll note we were able to assume that exactly the right amount of NaOH and HCl are present because this is a titration. So the point of a titration is to react exactly the right amount of acid to base so that you can get a neutral solution, and hence the word neutralize. Sorry if it's being loud here. I can't find a quieter place. Okay, so that means if you're neutral, that means you can't have any excess, because if there is a little bit of excess NaOH, then you're going to have a basic solution. Neutral means neutral like at pH 7, right? So if it was basic, then that would be above 7. If you had extra carminic acid left over, then you would have an acidic solution, so below 7. So the fact that you're neutralizing means you're reacting exactly the right number of a base to acid to, completely react without having any excess. So yeah, that was important for kind of processing this problem. So I just want to make sure you're aware of that. Okay, but yeah, with that, we're done with these 4 problems. I am so sorry I couldn't get these done earlier. Trying to figure out how to do these in a way that didn't take up too much time. Took up a lot of time, so I don't know if I really gained out of that, but hopefully by the time I see you in class later today, then we will have a YouTube link for this, and also I'm planning to do hopefully a Q&A session on here and the YouTube channel later on tonight, just to kind of test out if that's something that works or would be convenient for you, especially with the exam coming up. I definitely like a way to get as many of your questions answered as possible. So yeah, hopefully I'll see you tonight for the live stream, and if not, I'll see you in class, I guess. All right, well, have a good day. Bye.